Now this is a very important concept, mutarotation. Mutarotation is the change in the optical rotation because of the change in the equilibrium between two anomers. Mutarotation was first discovered by French chemist Fort in 1844 when he noticed that the specific rotation of aqueous sugar solution changes with time. A solution of ordinary D-glucose, which has the melting point 146 degrees centigrade, has an initial specific rotation of 112 degree, but ultimately the specific rotation of this solution falls to 52.7 degree. This also must be a plus. You cannot indicate a specific rotation by only the value. You have to give the sign also, plus or minus. A solution of the second form of D-glucose, which has the melting point 150 degrees centigrade, has an initial specific rotation of plus 18.7 degree. But slowly the specific rotation of this solution rises to plus 52.7 degree. That means if you take the alpha D-glucopyranose, which has the optical rotation plus 112 degree, or if you take the beta D-glucopyranose, which has an optical rotation plus 18.7 degree, both will give this, not this, sorry, both will give the optical rotation as 52.7 degree. That means something is happening which are converting these two into one another. This change in specific rotation toward an equilibrium value is called mutarotation. Now I have shown a chart where you can see in case of glucose, in case of equilibrium, the alpha contains 36% and beta form has 64%. That means in equilibrium 36% alpha and 64% beta anomer is present. In case of galactose, there are 27 to 36% alpha anomer and 64 to 73% beta anomer, and different values for allos, altos, idos. You can see this all thing you can check. Now mechanism for the acid catalyzed mutarotation. If you give acid, it can show mutarotation. Now what is the mechanism? You are giving acid, means H3O plus. Now if this oxygen will take the proton, and this oxygen will be, the ring oxygen will be protonated first, then a open chain form will occur. This bond is being broken. Okay, just give me 1 second. Okay, this bond is being opened and you are getting the open form, this one. Now this open form is in equilibrium. That means this can show rotation. So if it rotates, then you will get both the alpha and beta form. If it rotates in this way, if this bond rotates, you will get this one after rotation, and after the ring closure you will get this form. That means if you started with alpha D-glucopyranose and you are getting beta D-glucopyranose via a rotation of bonds. Now see very carefully what is happening here. At first this oxygen is taking the proton, then the ring is being broken, after that a rotation is occurring, then this oxygen is making ring again, and this OH leaves, then you are getting the beta D glucopyranose structure. This proton leaves, after the deprotonation you are getting beta D glucopyranose. Mechanism for the base catalyzed mutarotation. Now if you give base, in case of basic medium, there is also mutarotation possible. At first this OH will take this OH from the base, will take this proton which is in the anomeric OH. The base will take this proton, so this oxygen will become minus, and after that the oxygen will give the electron in this CO bond. Then this bond will be broken. Okay, this bond will break, and after that you will get a open ring structure. Now again a rotation can occur in this bond, a rotation can occur, and after rotation the carbonyl group which was in the bottom will go in the top, that means in the upper side, and this hydrogen will come here after the rotation. Now if this oxygen attacks here, the OH will group form here, that means O minus. Actually it is in the basic condition, that's why this will form O minus, not OH. And after the protonation, or if you add some water, this O minus will take a proton from here, and then you will get the beta D glucopyranol structure. So again alpha to beta in case of base catalyzed mutarotation. Now mechanism for the acid base catalyzed mutarotation. If you add both acid and base, their mutarotation is possible. At first what you are doing, at first this is taking this water is taking the hydrogen. Now here the acid base means you are taking water which can act as acid as well as it can act as a base. So water is taking this hydrogen at first, so this is becoming O minus, this O minus is attacking, and this bond is being broken. After the bond being broken, this oxygen is taking a proton from the water. Try to understand this. Then the bond is being rotated, this O ketone group is going in the up, and this OH group is going in the down. Then again this oxygen is giving its lone pair here, attacking the carbonyl group, and you are getting beta D glucopyranols. Do these all reactions, draw these all, and try to understand. The absorption spectra in aqueous solution indicate the presence of open chain forms. According to Lowry, mutarotation is not possible without the presence of an amphiprotic solvent, that is, a solvent which can function both as an acid and a base, such as water. Thus Lowry and Faulkner showed the mutarotation is arrested in pyridine solution, which is actually basic solution, and in cresol solution, which is the acidic solvent. But it takes place in the mixture of pyridine and cresol. So if you take individually the pyridine or cresol, that will not show the mutarotation. But if you take a mixture of pyridine and cresol, that will show the mutarotation. Let's see the mechanism in the presence of pyridine and phenol. So you have taken pyridine and phenol in the same mixture, reaction mixture, and you are also taking alpha D glucopyranols. So what will happen? The pyridine is a base, so at first the base will attack this anomeric OH and will take up this proton. So this oxygen will become the minus, then this minus charge will give its electron to the C and O bonding, that means it will make C double bond O. This bond will be broken, this bond will be broken, and this O will immediately take a proton from this phenol. So you will get this open structure, open ring structure, and again there is a possibility of bond rotation. So if this bond rotates, this carbon will go in the top, this hydrogen will go in the bottom. Now again this phenol, that means the conjugate base of this phenol, will take proton from this OH. That means this is the phenoxide ion. This phenoxide will take a proton, this oxygen will become minus, this minus will attack this carbonyl, this minus will attack the carbonyl, and this will open, so this oxygen will take this proton from the pyridinium salt. Then you will get the beta D glucopyranose. I hope you can understand this reaction mechanism. Now the mutarotation is also possible in case of 2-pyridinol. Since 2-pyridinol is an acid-base catalyst that gives proton to the acetyl oxygen while removing H+ from anomeric hydroxyl group in a synchronous manner, mutarotation occurs readily in the presence of 2-pyridinol. In case of 2-pyridinol, at first this nitrogen lone pair will attack this anomeric OH and take up a proton. Then this OH bond will be broken, this oxygen minus will give its electron to this C single bond O and it will make C double bond O. So simultaneously this bond will be broken and this oxygen will take a proton from this OH group of the 2-pyridinol. So all of these things are happening simultaneously. Then কি পাচ্ছি রে বাবা, then আমরা open chain ফর্মটা পাচ্ছি. That means we are getting this open chain form. তারপর কি হচ্ছে, তারপর বন্ডটা রোটেশন হচ্ছে, এই বন্ডটা ঘুরে যাচ্ছে, and उसके बाद क्या हो रहा है, उसके बाद this oxygen, actually this is taking the proton from here, ये ऑक्सीजन माइनस हो रहा है, अब ये माइनस इसे अटैक कर रहा है और उसके बाद ये कार्बोनिल ग्रुप का भी कार्बोनिल ग्रुप इस प्रोटॉन को ले रहा है. अब मेरा हिंदी बहुत ख़राब है, माई हिंदी इज़ वेरी बैड, दैट्स वाई आई हैव टू स्पीक इन इंग्लिश a little bit better, I hope so. So similarly you are getting this beta D glucopyranose. This is actually all the case of mutarotation. If you take alpha anomer, you will get a mixture of alpha and beta, and if you take a beta anomer, you also will get a mixture of alpha and beta. So this is the actual funda of mutarotation. When beta D fructopyranose, which has an initial specific rotation of minus 133.5 degree, is dissolved in water, it undergoes rapid mutarotation to minus 92 degree. Okay, so आप this beta D fructopyranose को ले रहे हो और उसके बाद म्यूटर रोटेशन हो रहा है और ऑप्टिकल रोटेशन जो है वो कम रही है, मतलब कम हो गया है. This mutarotation involves equilibration to both pyranose and furanose forms. ओहो, क्या हो रहा है यहाँ, पायरानोज और फ्यूरानोज दोनों फॉर्म ही एग्जिस्ट कर रहा है. तो ये है आपका डी फ्रुक्टोज and you are taking beta D fructopyranose. At first this is converting into the open chain structure, then into the alpha D fructopyranose, as well as you are getting the fructofuranose alpha and beta D fructofuranose structure. So you are getting all these structures together, and you can see these percentages. Beta D fructopyranose has the 57% contribution, whereas the beta D fructofuranose has 31%, and these alphas are 9% and 3% in equilibrium. The NMR spectroscopy has been one of the primary techniques that chemists have used to determine the ratios of the various forms of monosaccharides in solution. Since the two pyranose forms are diastereomers, we could expect them to have different proton NMR spectra. However, since they are in equilibrium with each other, an NMR sample of D-glucose will contain both forms and peaks from each will be seen. ओहो ये तो बहुत ही मतलब इम्पोर्टेंट चीज़ है, बहुत ही गुरुत्वपूर्ण, सॉरी क्या हिंदी तो नहीं है, ये बेंगली ही हो गया। এটা খুবই গুরুত্বপূর্ণ জিনিস। তো কি হচ্ছে, এই আলফা অ্যানোমারের হাইড্রোজেনটা, দিস is giving peak at delta is equal to 5.21 ppm. So ये सब तो NMR का है डाटा, I will discuss it later if I make any video on NMR, but now I am just telling it in brief. This proton will give the delta value 5.21 and this proton will be at the delta value 4.63. And the J here, J is the coupling constant, the coupling between this 1H and the 2H. The coupling constant is greater for the beta NMR. In case of beta NMR, the coupling constant have the value 7.9 Hz, whereas the alpha NMR has the value 3.8 Hz. So try to remember this all in case of mutarotation. The concentration of open chain D-glucose in solution at equilibrium is very small. Solutions of D-glucose give no observable UV or IR absorption band for a carbonyl group, and solution of D-glucose give a negative taste with Schiff's reagent, a special reagent that requires a relatively high concentration of a free aldehyde group rather than a hemiacetal in order to give a positive taste. Assuming that the concentration of the open chain form is negligible, one can, by use of the specific rotations in the preceding figures, calculate the percentages of the alpha and beta anomers present at equilibrium. These percentages comes out to be 36% alpha anomer and 64% beta anomer. These are in accord with a greater stability for beta D glucopyranose. As the beta D glucopyranose is much more stable than the alpha anomer, that's why it has the higher percentage. The beta anomer of a pyranose is not always the more stable. However, with D-mannose, the equilibrium favors the alpha anomer. So in case of glucose, you can see that beta D glucopyranose has the higher stability. That's why it is 64% at equilibrium and the alpha is 36%. But in case of mannose, beta D mannopyranose has the 31%, but the alpha D here, this one is the more stable, which has 69% in the equilibrium, because this OH and this OH are in trans, whereas this OH, these two feels some repulsion between them. Determination of the percentages of alpha and beta anomers of glucose present at the equilibrium. So let the mole fraction of alpha anomer is A and the mole fraction of beta anomer is B. Since the rotation of the mixture is plus 52.7 degree, we can write that the sum, that we have the A fraction beta D glucopyranose, so A into 112 plus B into 18.7 will give this 52.7. A fraction, okay, this is not actually 36 or 64, this will be the fraction smaller than 1. There is very little of the open chain form present, so the fraction present as the alpha and beta anomer should account for all the glucose. That means we are neglecting the open chain form, and that's why we are getting a relation A plus B is equal to 1. The alpha D and beta D will contain all the glucose in case of equilibrium. We are assuming that. and then we are substituting B by 1 minus A. So we get this, and after a very short calculation, you all can do it yourself. You will get that the A will come out to be 0.36 and B will come out to be 0.64. So therefore at equilibrium the amounts of alpha NMR is 36% and beta NMR is 64%. How the two anomers of glucose can be separated? This is a big question, that how you can separate these two anomers. When glucose is crystallized from water at room temperature, pure crystalline alpha D glucopyranose is obtained, and when glucose is crystallized from water, letting the water evaporate at a temperature greater than 98 degrees centigrade, crystals of pure beta D glucopyranose are obtained.